Hello, today we're going to look at digital imaging for A-level physics. We have a system of numbering called the decimal system. There are 10 numbers available to us, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and when we get to 9 we've used up all the numbers, and so the next number has to be a combination of numbers we've already used before. That's the decimal system. When it comes to digital systems, we use what's called the binary system, and we are restricted to just two numbers, 0 and 1, off or on. And so if we're going to number using the binary system, then of course we're okay for the first number, 0, and we're okay for the second number, 1. But when we get to 2, we're not allowed to use 2, so we now have to use these numbers again, and the next available number is 10. And then we can use 11 for 3, but we can't use 12 for 4 because 2 is not available, so we now have to go up to 100. So 100 is 4, 101 is 5, 110 is 6, and 111 is 7. Now we have to go up to 1,000. And 1,001 becomes 9, and 1,010 becomes 10, and so on. And it turns out that if you go to a number which is 8, each of these is called a bit. So this is 1 bit, 1 bit, 2 bits, 2 bits, 3 bits, 3 bits, 3 bits, 3 bits, 4 bits, 4 bits, 4 bits, because there are 4 bit numbers, 1 or 0. If you go up to 8 bits, and the maximum you can have is 11111111, that is equivalent to the number 255. And since you've also got 0, that means you're given 256 alternatives using what's called an 8-bit number. And we have a special name for an 8-bit number. It's called a byte. And that is information that computers use. The number of alternatives available to you, in other words, the number of alternative combinations of 1 and 0 that's available to you, doubles with each additional bit. Let's have a look. When you only had 1 bit available, you could only have the two numbers 0 and 1. So when you had 1 bit available, you could have 2 numbers. When you got 2 bits available, you can have 1, 2, 3, 4 numbers. So 2 bits gave you 4 numbers. When you have 3 bits available, you can have 1, 2, 3, 4, 5, 6, 7, 8 numbers. So 3 bits gives you 8 numbers. And you can see what's happening here. You're always getting double the number of alternatives for every additional bit. So 4 bits will give you 16 alternatives, 5 bits gets you 32 alternatives, 6 bits gets you 64, 7 bits gets you 128 alternatives, and then, as I've just shown you, 8 bits gets you 256 alternatives. And the general formula for this is that the number of alternatives is equal to the number 2 times, we call it I, and I is the number of bits. So just to show you that that was right, if you take 3 bits, then you would have 2 cubed, which is 8, and that's exactly what we showed. If you have 5 bits, then you have 2 to the power 5, which is 32, and that's what we showed there. So if you want to know the number of alternatives, then you simply take 2 to the power I, where I is the number of bits. Or you can, of course, take the logarithm of both sides, and if you take logarithm to the base 2, then you'll get logarithm to the base 2 of n, where n is the number of alternatives, is equal to logarithm to the base 2 of 2 to the I. Well, I comes down on the outside, and that becomes I times log to the base 2 of 2, which is 1. So now you've got a formula that says that log to the base 2 of the number of alternatives is equal to the number of bits. So let's suppose we want to know how we could encode the alphabet into bits. How many bits would we need to do that? Well, there are 26 characters in the alphabet, so 26 is our number. We need 26 different alternatives in order to uniquely define A and B and C and so on. And so we would simply say that we need log to the base 2 of 26 will equal the number of bits we need. And that actually comes to 4.7. Well, you can't have 4.7 bits, so essentially you would need 5 bits. And as you can see from the chart we showed before, that's right, because if you have 5 bits, you have 32 alternatives. We actually only need 26. Whereas if you'd had 4 bits, you would have had some letters that you couldn't have reproduced because you'd only have 16 alternatives and you need 26. Now, the way that a digital photograph works is that you take the photograph and you divide it up into what are called pixels, which means that there are lots of little elements of the picture. We shall see how many in just a moment. And the point is that every single pixel has one colour, and that colour is represented by some information contained in bits. So if you think about it, if you want a black and white picture, you could have 256 shades of grey, and you would only need 8 bits, or 1 byte, for each pixel. So that each pixel with 8 bits, typically you use the number 00000000, that's 8 bits. That would be black. And then 11111111 would be white. And all the other 254 options or alternatives that exist between these would be varying shades of grey, but they would start from black and they would go from very dark grey right the way down to light grey and finally to white. And so each pixel would contain one 8-bit number that would represent and could be converted by a computer, for example, into a colour, in this case a grayscale colour, and you then construct your picture using these bits. Now obviously the more pixels you have, the more detail you can get into the resolution of the picture. If you want colour, then typically what is included in a colour system is information about the extent to which each of the primary colours contributes to the colour in one particular pixel. And that usually means that you need to know how much red, how much green and how much blue there is in each pixel, and that will determine precisely the shade of colour that you want in that pixel. And we'll come on to the consequence of that in just a moment. But let's just explore what you can do if you have a picture made up of pixels. I'm going to take just 9 pixels, a 3x3 for illustrative purposes, and I'm going to use decimal numbers just so we don't confuse ourselves. So I'm going to have a picture which is made up of numbers like this. 4, of course, would in fact in binary be 10. It would be 100. 2 in binary would be 10, but I've used decimal to keep it simple. And the idea is that the higher the number, as the number increases, the picture gets lighter. So obviously 4 is lighter than 2. So this picture would be a light grey around the outside and a dark grey in the middle. Now, what computers can do very easily is number manipulation. So you could simply ask the computer to double the numbers in each case. So what we would now get is a picture where the numbers would be 8, 8, 8, 8, 4, 8, 8, 8, 8. That's just doubling what's here. Computers do that very easily. Now what will have happened? Well, because we've got the numbers higher, they will be lighter. So this will now be a very light grey, but that will now be a darker grey In other words, what we've done is we've improved the contrast. The difference between 2 and 4 is very small. The difference between 4 and 8 is much larger. So the contrast between these two pictures will have been increased and improved. So you can increase and improve contrast with digital images very easily. You can also use a device called false colouring to improve a clear difference. So suppose we had the picture we had before, where we have 4 all round the outside but only 2 in the middle. So we would say that this was light grey and this is darker grey. What we could simply assign is that 4 equals green and 2 equals pink. Now, you might not be able to see quite so clearly a dark grey against a light grey, but you would certainly see a pink against a background of green. So once again, we can, as it were, enhance the picture by assigning different values to the numbers. Once we've got numbers, we can do anything with it. And we can also reduce noise. No picture is ever perfect. One always gets spurious bits of information coming in. So let's suppose we've got a picture, this is a part of a picture, where the decimal values are 2, 3, 2, 1, 2, 2, 2, 1, but in the middle we've got a rogue value of 12. That got in there somehow, maybe a stray piece of light suddenly hit the screen. It shouldn't be there and it's going to distort the picture. What you can do is you can tell the computer to go through all the numbers in all the pixels and to replace each number by the median of itself and the surrounding 8 numbers. All pixels will, of course, if we take this pixel here, they will all be surrounded by 8 other numbers. And the median is the middle. It's not the average. If you take, we've got 9 numbers, and what you do is you simply take the 5th highest, and that's the median. Well, in this case, you can see that the 5th highest is going to be 2. And so 12 would be replaced by 2. And that's a way of getting rid of some of the more extreme values that are almost certainly going to be spurious. There is a system called the Laplace rule, which is a means of determining edges where they are not clear. This time I'm going to take a set of pixels 6 by 4, and we're going to have the values 6 in this half and the values 2 in this half. And although it's pretty obvious to us that the edge is along this line here, this will be light, this will be dark, because remember, the higher the number, the lighter the colour, the lighter grey. Let's assume this is a grey scale. But it may not be too clear. If we're talking about values from 0 to 256, the difference between 2 and 6 might not be that obvious. But once again, we can use, because these are numbers, we can get computers to sort it all out for us. And what we ask them to do is, for each pixel, you take the number in the pixel, so we call that the number p, and you multiply it by 4, and then you subtract from it the value in the pixel above, the value in the pixel below, and the value in the pixel to the left, and the value in the pixel to the right. So you take any pixel, take this one, 6, multiply it by 4, and then subtract the values above, below, to the right, and to the left. Now what do you do? What do you get? Well, let's start off by looking at this pixel here. That's got a 6 in it. So we would multiply 6 by 4, that's this rule here, and then we subtract the values above, below, and right and left. Well, above, below, right and left are all 6s, so it's -6, -6, -6, -6, and that comes to 0. 6 4s minus 6 lots of 4 is 0. And 0 is black. So this pixel would become black. What about this pixel here, the 2 value? Well, again, you do the rule 2 times 4 minus the values above, below, right and left, and they're all 2s. So it's 2 times 4 minus 4 lots of 2, and that 2 is going to be 0, and that's going to be black. So this will become black. But what happens when we get a value here, which is on the edge? Well, now we're going to have, you multiply that value by 4, so it's 6 by 4, minus above, below, right and left. But here we've got above is 6, below is 6, to the left is 6, but to the right is 2. So it's going to be minus 6, minus 6, minus 6, minus 2, and that's going to be 4. And so that pixel is going to be not black, it's going to be a grey colour. And so what you'll actually see on your screen is that all of the pixels that aren't at the edge will be coloured black, but you'll have a much lighter value at the edge. So if you need to determine where the edges arise, then the Laplace rule is the way to do it. So let's consider the picture that you might draw, you might take from your camera. This is relatively small for cameras these days, but you might have 1,000 pixels across, or rather 1,000 by 600 pixels, so 1,000 divisions this way, 600 divisions this way. Each of the little squares that is caused by those divisions is called a pixel, and what essentially you're doing is each pixel will have a number in it. For black and white, it is sufficient to have 1 byte, because 1 byte is 8 bits. 8 bits will give you 256 bits of information, and that means you can have any shade of grey from 0, which is black, to 256, which is white, and 254 shades of grey in between. And if you were to have, this would be then 600,000 pixels, each of 1 byte, so that would be 600,000 bytes per photograph, which is of course called 600 kilobytes. That's the way we express it. So that picture would be a 600 kilobyte picture. But of course, if you're looking for colour, then you're going to need more than 256 variations, because you need all the colours and shades as well. TVs typically use 65,536 colours. That's all the different alternatives or shades. And if you take the formula that we got before, which is that the number of bits required is equal to the log to the base 2 of the number of alternatives you need, 65536, you'll find that log to the base 2 of that number is 16. So you need 16 bits per pixel in order to have 65,536 shades of colour. And of course 16 bits, since there are 8 bits to a byte, is 2 bytes. So for black and white, you only need 1 byte per pixel, and that gets you 256 shades. But if you give 2 bytes per pixel, then you get the ginormous 65,536 different types of colour. And that means, of course, that your byte size will increase. Instead, if you want a 600 by 1,000 picture in colour, each of those 600,000 pixels will need 2 bytes, and consequently your picture size will not be 600 kilobytes anymore, but twice that, which is 1.2 megabytes. So that's starting to get a large picture. And of course 600 by 1000 is now quite small in picture terms. Cameras will take much finer resolution than that. And consequently the size of the pictures, which is determined by the number of pixels times 2 bytes, because you need 2 bytes for each pixel, the size of the picture increases dramatically. The next number has to be a combination of numbers we've already used before. That's the decimal system. When it comes to digital systems, we use what's called the binary system, and we are restricted to just two numbers, 0 and 1, off or on. And so if we're going to number using the binary system, then of course we're okay for each of these is called a bit. So this is 1 bit, 1 bit, 2 bits, 2 bits, 3 bits, 3 bits, 3 bits, 3 bits, 4 bits, 4 bits, 4 bits, because there are 4 bit numbers, 1 or 0. If you go up to 8 bits, and the maximum you can have is 1111, 1111, that is equivalent to the number 255. Hello, today we're going to look at digital imaging for A-level physics. We have a system of numbering called the decimal system. There are 10 numbers available to us, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and when we get to 9 we've used up all the numbers, and so then 110 is 6 and 111 is 7. Now we have to go up to 1,000, and 1,001 becomes 9, and 1,010 becomes 10, and so on. And it turns out that if you go to a number which is 8, the first number, 0, and we're okay for the second number, 1, but when we get to 2 we're not allowed to use 2, so we now have to use these numbers again, and the next available number is 10. And then we can use 11 for 3, but we can't use 12 for 4 because 2 is not available, so we now have to go up to 100. So 100 is 4, 101 is 5,